All right, so let's take a look now at derivatives. And we're going to be looking at derivatives of functions in two variables. And we're going to introduce something called the partial, or the partial derivative. And so here's our definition of the partial derivative. We're going to let f of xy be a function of two variables. Then the partial derivative of f with respect to x, written as df dx, or fx, is defined as, and this is df dx equals the limit as h approaches 0 of f of x plus hy minus f of xy over h. And then we'll have separately something called the partial of f with respect to y, written as df dy, or fy, is defined as, and this is df dy equals the limit as k equals 0 of f of x y plus k minus f of xy over k. Okay, so a couple of things that I actually want to point out here as we're working. One is that we've got the partial with respect to x, and then we're also going to have a partial derivative with respect to y. So we've got two separate variables here for the single function. And we're going to talk about that a bit more in depth. Basically what's going to happen here is we're going to imagine that we're going to be just looking at the function in, say, for example, the xz plane or the yz plane. Right? If you imagine f of x, y as being z, then you can kind of imagine that, you could pull the function away and look at it, right? Okay, like we did when we were doing, when we were working with the graphs, as a function just inside of that plane. Okay, and just kind of consider what happens to the function z as x changes, or what happens to the function f as y changes. Okay. And what that means for us from a computational perspective is it means that we are going to be looking at what happens when we keep y constant and then we let x change, or when we keep x constant and we let y change. All right, and that's why they're called partials. They're called partials because what basically we're going to do is we're only going to be looking at the rate of change with respect to one variable at a time. Right, so we want to know rate of change with respect to one variable at a time. If you can kind of remember that, then everything that we do with respect to partial derivatives actually gets kind of easy. All right, it's much easier than what we were doing in calculus, where we had to go out and you had to learn everything, right? You had to learn all those techniques of finding differentiation, finding derivatives. In this case, it's all the same techniques. All the techniques are the same. What we're adding in is we're adding in this wrinkle of, well, what happens if I have another variable? And it doesn't really actually make things all that much more difficult, okay? Because we're just going to treat the other variable as if it's constant. And we're going to do that no matter how many variables we actually have. But we're going to just start out with that in two variables. So let's actually go and use that definition of the derivative to find, and I want to note the notation here, this df dx df dy. We have this df dx, and notice it's not actually a d, it's kind of this curvy d, and then df dy. All right, and notice derivatives with respect to different independent variables. All right, so notation difference. And what we're going to do is we're going to use the definition of the derivative to find these two for f of xy equals 4x squared plus 2xy minus y squared plus 3x minus 2y plus 5. Now, if you're in my class, I'm not really going to have you actually use this definition of the derivative in order to go out and find these partials. What I'm really chiefly interested in is I actually kind of want to demonstrate what it looks like to treat one of the variables as if it's constant, and then what is the effect of that when we actually take the derivative, okay, or take the partial derivative. Because what you'll see is that it kind of, like, if we can kind of start thinking in this way of thinking about that variable as constant, it makes everything a lot easier when you're actually finding the partials. So let's actually do this. And so remember that our definition here is going to be df dx is going to equal f of x plus hy minus f of xy divided by h, and actually we're going to be taking the limit as h approaches 0 for that function, for that difference quotient. So everywhere where I have an x, I'm going to plug in x plus h, so I get 4 times x plus h squared plus 2 times x plus h y minus y squared. And notice with the y's, I'm just going to plug in y. So it just stays y minus y squared plus 3 times x plus h minus 2y plus 5. And then I'm going to subtract from that, because I'm going to be taking the limit as h approaches 0 of this, minus 4x squared plus 2xy minus y squared plus 3x minus 2y plus 5. All divided by h. Okay? Now a couple things to notice. First things first, if there's no x's in the part of the function that we're looking at, notice that I'm going to have a minus y squared and I'm going to have a minus y squared. So those two, they're actually going to cancel. Okay? And then I have a minus 2y, and I have a minus 2y right here, and they're also going to cancel. And then also the constants cancel. We know that that's what happens anyways whenever we take the derivative. So what's essentially happened here is that anywhere where we have just the function, just a function of y, or a piece of or one of the terms is just a term of y only, no x's, it goes away. It's actually going to be removed because we're going to subtract it out with that definition of the derivative. Now what we do is we see, okay, so now I'm going to get 4 times x squared plus 2xh plus h squared plus 2xy plus 2hy, because notice we've got that y there, okay, and then plus 3x plus 3h, and then we'll actually subtract minus 4x squared minus 2xy minus 3x, and that finishes it out. We're going to take that divided by h, and we'll take the limit as h approaches 0. Okay? So now, I mean, you've seen this before, and now that you've probably done this so many times. 4x squared, the 4x squareds, they're going to cancel. Okay? My 2xy is going to cancel as well, right? Anything that doesn't have an h, it goes away. Okay? And now what we're left with is 8xy plus 4h squared plus 3h, all divided by, plus 2hy. Okay, so 8xy plus 4y squared plus, and that's our 2hy plus 3h, all divided by h. Let's check and make sure, right? 8xy, 4h squared, 2hy, 3h, and nothing else, okay? We'll take the limit as h approaches 0. We're going to factor out our h's. We'll end up with 8x plus 4h plus 2y plus 3. And we'll take the limit as h approaches 0. And so that ends up giving me 8x plus 2y plus 3. And that is our partial derivative. So a couple things to note here. One is if you just took the derivative with respect to x, 4x squared would just give you 8x. So that's exactly what we expect. Now, let's imagine that y is being treated like a constant, like it's just 2 times y. Okay? And you can imagine, oh, well, what if it's a 3? Well, then it would be 6, right? And what would we get? We would get 6 when we take the derivative of 2xy. Okay? Or, in this case, 2y, because we're only dealing with x as the actual variable. So take the derivative with respect to x only, okay? And that just leaves you with the 2y, using just our power rules. And then finally, we've got a 3x, and so the derivative of that is going to end up being 3. And there we go. And so actually what you can see here is that's what we're talking about when we're talking about treating our variable, right, y as a constant. Okay, let's see what happens when we go in and we treat x as a constant. All right, let's take, for example, we've got g of xy equals sine x squared y minus 2x plus 4. Let's find dg dx and dg dy, okay? And so now let's see what happens when we're not actually going to use our definition, right? Because it's the sine function. Well, if I think about this, what I've got here is I basically got a chain rule. right? My outer function is cosine, sine, so that becomes cosine, and it'll become cosine x squared y minus 2x plus 4. That's just not gonna change, right? You take the derivative of the outside, you plug in the inside, great. Now what we've got to do is we actually got to go in and we got to take the derivative of the inside part of our function. And so this is now what we're going to see here, since we're doing dg dy, okay, we're going to treat the y as the thing that's changing and the x as a constant. So x squared y, I mean, like, you're like, well, what's the derivative of x squared y? Well, if you had 2y and you took the derivative, ddx of dy, excuse me, of 2y would just equal 2. Well, that's kind of the same idea here, or it's exactly the same idea. dy of x squared y is just going to equal x squared. Okay? Because the y, you've only got one of them, right? What do? We use the power rule, we subtract 1, okay? And we just end up keeping the scalar. So that gives me x squared. Now I look at this and I go, oh, well, what about minus 2x? Well, there's no y's in minus 2x, so actually minus 2x acts as a constant, so there will be nothing there in addition. And what about the 4? Well, the 4 is a constant, so when we take the derivative of the constant, it ends up being 0. So we just have that. We're going to have x squared cosine x squared y minus 2x plus 4. And that is our partial with respect to y. What about dg dx? Well, dg dx now, what we're going to do, we've got to use that chain rule again. So we've got cosine, and it'll be x squared y minus 2x plus 4. And now we're going to do something a little bit different here. We're going to do it with respect to x now. So if I look here, all right, what would ddx, okay, of x squared y be? Well, the y is like a scalar, right? It's like as if it was like a 3. So we're going to have, that's going to equal y times, and then the derivative of x squared, y times 2x, which is just 2xy. So we're going to multiply that by 2xy. Then we take the derivative of negative 2x, so minus 2. And the derivative of 4 is still 0. Okay? If we write this correctly, we should write it as 2xy minus 2 times, and we put the cosine second, x squared y minus 2x plus 4. Okay? So what you can see is that our rules for taking derivatives actually carry over, right? Now, but now when, say, for example, if we take, the derivative of the inside, we are going to have to, start treating the other variable as if it's a constant. And that's what we mean by treating the other variable as a constant. All right. Now, we're going to talk about the partial derivative graphically, and let's hope that this works. It is a tricky idea. You kind of have to sit down and think about it. What you want to do is you want to still consider the derivative to be a tangent line. But remember what I said, when we're taking the partial, we're going to treat one of the variables as if it's constant. The problem is that in the actual graph, it's not actually being held constant. It's changing. So let's imagine that I have a curve in space, right? I've got this function that is a function of x and y. So I've got that curve there, okay? And it's just moving in space. And what we want to do first is we want to say, well, what happens, right? Whenever I think about this curve, I can think about it that it moves, it goes a certain amount in the x direction and it goes a certain amount in the y direction, right? Okay. Or it changes as we change in the x direction. So say, for example, here's our x direction, right? There's our x-axis, here's our y-axis, here's our z-axis. So let's imagine that I take here, this point right there, okay? And I want to imagine what we're going to call it, and we'll like fx here. So here's my function f of xy. And I want to imagine what happens with fx. Now, what we're going to do is we're going to imagine only that we're moving, we're going to be moving along this x-axis, so we're going to hold the y value, whatever this y value is right here. So we'll move down, and we want to imagine, okay, we're going to kind of hold that y value constant. Is it constant? No, it's not constant, but we're just going to imagine that we do exactly that. And then we're going to see, well, what happens with respect to z as we move along the x. Right? Okay. So how much changes with just respect to the x? And so we say, all right, well, there's kind of like our rate of change with respect to x if we held y constant, right? We kind of create a secant line, and what we're kind of doing, if you kind of remember we're going to kind of project this curve onto the plane, right? That is y equals whatever. Okay, so y equals whatever the constant value that we have there. We're going to project it onto that plane, and then we're going to imagine what happens to the graph, okay, with respect to just the changing in our x variables, okay, or just the changing in our x values. So you're like, okay, well, if I just look at what happens with respect to x, okay, there's the change in z over this amount of x, right? So this is the change in x. This would be x, and this is x plus h. Right, and we get like our z1, or yeah, our z1, our z1 and our z2, right? Okay, and that we just imagine that we've got that rate of change. So now, what happens though if we think about it with respect to y? All right, we want to kind of think back, and we're like, okay, well, what happens with respect to y? And again, like I said, stuff's tricky. So now, what's being held constant, okay, is our x value. All right, so again, I'm going to move down here, okay, but I'm going to say, okay, well, let's say, for example, that's the x value right there, okay, and we're going to be moving along. We want to see, okay, well, what happens? We're going to be moving in this direction along the y-axis, all right, and we'll get maybe, possibly, most likely, a different change in y. All right, there's going to end up being a different change in, a different change in z based upon that change in y along this axis, along that y-axis. All right, so we're kind of imagining again now. We're going to be in a plane, right? Okay, and you kind of imagine if you projected it up against the xz plane or along this plane x equals whatever, right? And then we just kind of figure out, okay, well, what is the graph going to look like along that plane? Right, and we'll get a y portion of the rate of change. So, and like I said, it's kind of hard to draw these graphs and to think about them. But basically, what we'd say is that fx, right, and that's just our alternate way of writing df dx, is the slope of the tangent line parallel to the y-axis. Right? We're just running in a plane somewhere parallel to that y-axis. And then fy, which is df dy, is the slope of the tangent line parallel to the x-axis. And basically, it's going to be, like, if we think about that, that's the rate of change in z if we don't change y. Okay, so how much does z change? If we're only changing x, we're not changing y. That's going to be our fx. And then our fy is going to be the rate of change in z if we don't change x. So if you kind of think about it, if we kind of like step back and say, okay, well, for example, when we work with vectors, if you remember inside like a vector, you always have an x component, you have a y component, right? Okay, or an x part or a y part. Well, same thing here. It's just that what we have is we have the rate of change that is committed to the change in the change in x, and then we have a rate of change that actually is committed to the change in y. Okay, and probably I should switch that change in y for df dx, and change into x if we change x, that's fx, and the rate of change in z with respect to y is our fy. Okay. And basically, like I said, it's kind of like the pieces of that overall derivative. If you kind of thought about breaking it up, right? If we broke up the derivative into two parts, into our x part and our y part, fx is the rate of change with respect to x, and fy is that rate of change with respect to y. Kind of a tricky idea. You'll probably have to sit down and think about it a little bit. Now, in order to help us to kind of illustrate this a little bit better, let's use a contour map, because what that's going to do is that that's going to take away one of our dimensions and help us to kind of at least partially think about these partial derivatives, pardon the pun, partial derivatives while kind of like simplifying the process. So let's say we use a contour map, and we're going to consider g of xy equals the square root of 9 minus x squared minus y squared, and we're going to estimate dg dx at the square root of 5, 0. Okay, at the square root of 5, 0. So where I'm going to start is I'm going to start out by actually drawing a couple values for the contour map. All right, okay, And so what we get here is, let's say, for example, I have c equals 1, all right, and I have c equals 2. And those are, we'll have those be our slopes, or we'll think about that as z equals 2. So that's going to be then, for c equals 1, we're going to get the square root of 9 minus x squared minus y squared equals 1. So that ends up giving me negative x squared, or well, square both sides, subtract 9, so this ends up being negative, square both sides, subtract 9, that becomes negative 8 equals negative x squared minus y squared. So we get x squared plus y squared equals 8. There you go. So that's a circle of radius 8, right? That's if c equals 1. So there's our circle. Let's just imagine that's a circle of radius 8. Okay. So there's c equals 1. Actually, pull that out, put that on the inside. And then when c equals 2, if you go through, do the same process, right? We're going to take square root of 9 minus x squared minus y squared, okay, equals now 2. Divide by 4, we end up with x squared plus y squared equals 5. All right, and so that ends up being here. Just a shade inward, right? We'll just draw our contour like that, okay? And that's c equals 2. Notice that with x squared plus y squared equals 5, what we get is we've got a radius, r equals square root of 5, and the radius for x squared plus y squared equals 8 is the radius of equals the square 2 root 2. Okay, so those are our two radii. Now let's actually, what we want to do, since we're trying to find dg dx, what we'll do is we're just going to actually consider this change. All right, if we hold, we're going to let y equals 0. So we're going to hold y equal to 0. We're going to keep it constant at y equals 0, which is something we can do. Okay, we could choose any value that we want for our y. All right, and in this case, it's really not going to matter too much. But in our case, let's choose y equals 0. And the reason why is it's going to make things really easy. So if y equals 0, we've got this point right here, and that point is going to end up being the square root of 5, 0. All right, that's on the line c equals 2. All right, and so radius is equal to root 5, so here's 0, right? You go out root 5, that's the radius, so root 5, 0. The second point, this one here on the circle c equals 1, is going to be the point 2 root 2, comma 0. Okay, and so that is our second point. Now, all we've got to do now is just calculate our rate of change, all right? Like what's happened here. Now, our z values, z here, if you kind of think about what are our 3 points here, we've got first for this inner circle, we've got the point 2, or excuse me, not 2 at the end. We've got the point root 5, 0, 2. X, y, and z. Okay? And then our second point is going to end up being 2 root 2, comma 0, comma 1. All right? Now thinking about it's a derivative, so we're going to do, and it's a derivative of z with respect to, in this case, x. Okay? So we got 2, we got 1. We're going to end up getting, it's going to be, or excuse me, 1 minus 2 divided by 2 root 2 minus root 5. And this is approximately equal to negative 1.688. And that is our rate of change. Okay? Kind of simple if you think about it. All right? You can pick whatever value you really want for for y in this case. We weren't told which one to choose. We chose the easiest one, that is that let y equal 0, so we just have to find x-intercepts. And the x-intercepts are just our radiuses. All right? But what I want you to see is I want you to see that the y didn't even play a role there, really. Okay? Because it's a 0 in this case. And what we did was we found it's the change in z, okay, divided by, in this case, the change in x, the dg dx. Right? If we wanted to actually find, if we wanted to go out and estimate dg dy, we could actually go through and do something pretty similar. And we would get, well, theoretically, we could actually get an identical answer. right? We would actually get the exact same negative 1.688 given this particular change in x. Or excuse me, this particular change in z. All right, so that's how we can kind of think about and use the contour maps in order to estimate our derivatives, right? What you'll do is you'll hold one of the variables constant, whichever one is the one that you're not taking your derivative with respect to. Then you'll calculate the values for x based upon the changes in z, and then just go through and find the difference quotient, right? Change in z or change in f, right, divided by the change in x or y. And there we go. Okay, so let's take a look at another way to kind of think about these partial derivatives and this whole idea of holding the one of the variables as constant. What we're going to do is we're going to take a look at this picture of this this function here, okay? And it's a function of x and y, so it's a function of two variables. And what we're going to do is we're going to calculate the sign of the derivative for particular values. So let's say, for example, I want to find f of x at 1, 1. Okay? And so that's the partial derivative with respect to x at 1, 1. So I'm going to start here and I'm going to notice, I'm going to go look out, and here's 1, 1. So 1, 1's right here on the curve. All right? And what I'm going to do is I'm going to hold my y's constant, so I'm going to be moving parallel to that y-axis. So I'm going to be moving parallel to the y-axis, so with respect to my x values, okay? So I'm going to change my x's, all right? And so as x increases, excuse me, I'm not going to be doing that. I'm going to be moving in the x direction. I'm going to hold my y constant, so the y is going to be held constant along this line y equals 1, pardon me, okay? And so if I look here, what's going to happen as x goes from 1 to 2, as I move in this direction, we'll be moving upwards. Okay, so the value, the z's are going to be getting bigger as we move along that line of y equals 1, or excuse me, that's negative 1. Y equals negative 1. So let's just make this negative 1, sorry. Y equals negative 1, and so the sign here is going to end up being positive. All right. What about f of y at 1, negative 1? So we'll start at the same place. F of y at 1, negative 1. And so now the 1 is going to be held constant. We're going to hold our x's constant. Okay? And if you look at the y's now, well, the y value, okay, we go from negative 1 to 0. So that's actually, you can see that it's actually going to be going negative. The z's values are going downward there. So this is going to end up being negative. Let's take a look at, we'll get f of x, and let's take 0, 0. And we want to know what happens with respect to the x's at 0, 0. Now you can kind of see, it's a little hard to see, but 0, 0 is right at the bottom here, and it's probably like at the trough. So it's at the very bottom here, okay? And if we hold our y's constant and we move just in our x directions, well, if I go, right, if I go in the negative direction, I'm going to end up having it be negative. If I go to the positive direction, I'm going to end up being positive. And the reason why is because that derivative there at 0, 0 is actually going to end up being equal to 0. So it's neither negative or is positive. It's actually going to be like kind of a minimum, right? On the other hand, if I take f of y at 0, 0, what we're going to get at then is we're also going to get something that looks like a 0 as well, a minimum there as well. We're going to be moving along x equals 0. Okay, and so this is also going to end up being 0. Let's take a look at one more. Let's take, for example, we'll take f of, and now let's do 1, 1. Actual or 1, 1 this time. fx at 1, 1. So now here's the 1, 1. It's going to be right about here. Okay, somewhere in that area, maybe right about there. Okay, and now if I hold my y's constant, all right, so I'm moving my x direction, what happens? You can see that that's going to be positive. It's moving upward. The z's are getting larger. Okay, so this is going to be positive. And let's take f of y at 1, 1. F of y at 1, 1, we're now going to hold our x's positive. And so what you can see here is that we're basically You see that slope of that tangent line now is going to end up being positive, so this actually ends up being positive. All right? And so this gives us another way to kind of visualize what does it mean to actually hold one of the variables constant while while taking the derivative at the rate of change with respect to the other. Okay, so now we're going to talk about something called higher order partial derivatives. We're going to look at them in two variables. And so let's say, for example, what this is basically, they equate to like taking the second derivative of a particular value, right? You're going to take the derivative of the first, you're going to take the first derivative and then you're going to take the second derivative. But we have to take the first and second derivatives with respect to particular variables, right? Because we've got more than one choice. And so in this case, since we've got two variables, we're going to have four choices for what are called our higher order, our second partials. Okay, our second partial derivatives. Now, notationally, we've got them, they look like this. So we're going to take, for example, we'll take the derivative of f with respect to x, and then we'll take the derivative of that with respect to x. And what we do is we write it as fxx. That actually allows us to do something like, to do this faster, or to write faster. Then if we took df dx, and then we took the derivative with respect to y, we get f of xy. So this is the first. We take the derivative with respect to x first, and the derivative with respect to y second. All right, so when we write that, that's actually the order that we write it in. Okay, now d dx, df dy, and this is going to be f of yx. All right, so again, we'll take y first, and then x second. And then d dy, df dy, and that's f of yy, so we took the derivative with respect to y twice. Okay? And so we get four theoretically different derivatives. What we're going to see actually is that as long as we have a continuous function on a disk of some sort, whatever disk that we're working at, then f of xy is going to equal f of yx. That the mixed partials, and that's what these two are called, they're called mixed partials. The mixed partials will be equal to each other. All right? Mixed partials are equal as long as they are evaluated on a continuous disk, or a smooth part of the curve. All right. Okay, so let's take a look at what that would look like if we had, say, a function. All right, and let's calculate our partials. So let's say, for example, I've got f of xy equals x e to the negative 3y plus sine of 2x minus 5y. Okay? And so we'll take that. And so what we'll do first is let's find fxx. All right? So we'll find f of xx. And so first I'm going to take the derivative with respect to x. And so that's going to be, so this is going to be d dx of, and we'll take the derivative with respect to x here. That's going to be e to the negative 3y. Plus, and this will be cosine and 2x minus 5y times 2. Okay? Great. Now I'm going to take the derivative with respect to x again. So e to the negative 3y is now just 0. All right? Because it's got no x's in it. So this is going to be 0 plus, and this is going to be 2 times, and this will be negative sine times 2x minus 5y times 2 again. And so what we end up with is negative 4 sine 2x minus 5y. And that is the second derivative, or that's fxx. That's the second partial with respect to x twice. Let's try fxy. So this is now going to be d dy, because we're going to take the partial with respect to y. And then we're going to take the partial with respect to x first. So again, here's the partial with respect to x. So that's e to the negative 3y plus cosine 2x minus 5y times 2. Now we're going to take the derivative with respect to y. So e to the negative 3y is going to be negative 3e to the negative 3y. Plus, and this will still be 2. We'll take the derivative of cosine, so that's negative sine. That's still the negative sine. 2x minus 5y is still the function within. but then we're going to be multiplying by negative 5. So what we're left with is negative 3e to the negative 3y minus 10 sine 2x minus 5y. So see, different, important. How about f of yx? Well, now we're going to take the derivative with respect to x, but first we've got to take the derivative with respect to y. Go back up here, x is now constant, so this becomes negative 3x e to the negative 3y plus, and then we've got cosine 2x minus 5y times 5. Great. Now we've got to take the derivative with respect to x. Well, if I look at this, notice that e to the negative 3y has no x's in it. Just the x here, we take that derivative with respect to that x, that's just 1. So this gives me negative 3e to the negative 3y. Then plus, and this will be 5 times, and then this is going to be negative sine, okay, negative sine, oh, this should have been negative 5, pardon me, that's negative 5 there. So plus negative 5 times negative sine, and this is 2x minus 5y, times now 2, because we're taking the derivative with respect to x. So this ends up equaling negative 3e to the negative 3y, plus 10 sine 2x minus 5y. Oh, remember what I said? Oh, and by the way, this should be plus. Sorry, drop it off those negatives. If you watch enough of my videos and be enough of my classes, you'll notice that sometimes the negatives go away as I'm talking. Apologize. I try and correct them. All right? So they end up being the same. Remember I told you that actually is going to end up being the same. That's actually kind of a really handy rule that's going to come in handy for us. Okay? And now let's take f of yy. Okay, f of yy. So we're going to have d dy of negative 3x e to the negative 3y plus, and let's just, or rather minus, 5 cosine 2x minus 5y. And when we take the derivative with respect to y of this, we end up with 9x e to the negative 3y. Remember, we're taking the partial with respect to y, minus, and then this is going to be 5, and then negative 5, so negative 5 times negative 5. So we'll take that minus 5 times negative 5 times negative sine 2x minus 5y. And so this is then 9x e to the negative 3y minus 25 sine 2x minus 5y. And that is our second partial, fyy. Okay? And so that's actually how we go in and we calculate our higher order partial derivatives. Okay? So higher order partial derivatives are basically, you're going to repeat the process. You just always have to keep in mind, okay, which variable that you're taking the partial with respect to. So let's end this lecture on partial derivatives for two variables with Clairaut's theorem. And so Clairaut's theorem actually states that we want to suppose that f of xy is defined on an open disk D. So remember, we're not like just on an open interval, we're actually looking at an open disk now. And it contains the points a, b. If the functions fxy and fyx are continuous on D, so as long as the partials are actually continuous on D, then f of xy is going to equal f of yx. All right? So the mixed partials will end up being equal to each other. This is going to end up becoming really handy for us later on as we do more and more work here in multivariable calculus. All right? So with that stated, we've gone through and we've actually kind of talked about quite a lot. We've talked about like the whole idea of the derivative, and the derivative being, or the idea of a partial derivative as one of the functions or one of the variables gets held constant while the other one changes. Okay, and we do that either with respect to x or we do that with respect to y. And then we also went over with partials, which is basically the process of doing that derivative twice, right? and making sure that you're taking the derivative with respect to each correctly. Okay? So this ends the lecture.